The talk here is building stateful clustered microservices with Java, actors, and Kubernetes. And I did a talk this morning, and I didn't really mention much about me. I work for a company called Lightbend. Anybody heard of Lightbend? Oh, some, okay. How about Scala? Heard of Scala? Scala is an object functional programming language. One of our co-founders of the company was the creator of Scala. And then with actors, and it was mentioned this morning in one of the keynotes, there's Akka, which is the actor model on the JVM for Java and Scala. And what I'll be kind of covering today is Akka running on Kubernetes and some other things. So this talk really is focusing, though, on something running on Kubernetes. And with Akka, one of its features is that things can run in a cluster. So that's what we'll be looking at. But just so you know, like I mentioned, my company, Lightbend, we have a bunch of people that work for Lightbend that are working on the open source projects for Akka, for Scala. And then there's another framework, it's called Play, which is a web service framework for Java and Scala. And it's been around for a while, and it's all asynchronous. It's always been asynchronous. So effectively, it's always been a reactive programming type of framework. And then there's a relatively new framework called Logom, which is a microservice framework. And it's built on top of Play and Akka. So it's kind of a way if you have developers that are new to microservices and want kind of a helpful pattern, kind of a guide rails pattern for how to implement microservices, doing things like event sourcing and CQRS, which I talked about this morning in another talk. Logom is a good framework for that, and Java Scala as well. But really, here, what I want to talk about is why Akka, the way I look at it is Akka loves Kubernetes. And the reason being is that Akka has had the ability to run in a cluster, meaning it could run on multiple machines, multiple JVMs that are tightly coupled with each other. They're talking to each other over the network and everything, but it didn't have the orchestration piece. That's not what we wanted to do. So we were dependent on things external to Akka to handle the actual running of the JVMs, like on multiple virtual machines or whatever. And then now we got something like Kubernetes is coming along where it's like the perfect platform to run an Akka cluster. So that's what we'll be covering here. But before we get into it, anybody used Akka or know of the actor model a little bit? Okay, cool. The actor model is really interesting. It's been around since the 70s. The concept was first defined in the 70s. And it's been in use in different ways, like Erlang is where it was most famously used, like in the 80s and the 90s and so on, and still now. And it was a form of the actor model. But the actor model itself is a conceptual model. It's really very interesting. So I grabbed this definition from Wikipedia. It's 2 or 3 sentences, and I think very nicely, concisely kind of defines what is the actor model. And Akka is an implementation of the actor model. So the actor model is don't let it scare you, but it says a mathematical model of concurrent computation. But we can really not concern ourselves with the mathematical model piece of it. But it does treat actors as universal primitives of concurrent computation, which is really interesting. And the idea is that actors are implemented in code. They're basically just a fancy form of an instance of an object. Like if you're writing Java, actor is using Akka. A instance of an actor is really a class that you've written, and same thing in Scala. But the actors themselves are typically fairly fine-grained, and they're kind of like, and the patterns of what you can do with them are fairly fine-grained. Actors, you can kind of think of them as like fundamental building blocks when you're building a system. Like objects are fundamental building blocks, but I kind of like to think of them like Lego blocks. Lego blocks, there's a very simple pattern for using Lego blocks to build something, but people build amazing things with Lego blocks, right? And it's the same kind of thing with actors. You can build really amazing systems using some very fundamental capabilities of what an actor is. So the big thing with an actor is that the only way that you can communicate with an actor is by sending it an asynchronous message. And when an actor receives a message, it makes local decisions. So it's kind of like, the analogy I like using is texting. You and I are texting. So when we're texting each other, we're sending each other asynchronous messages. And when it's fun, one of the things I like about building actor systems is fun to do it with a colleague, because we can pretend to be two different actors. Like I'm actor A and you're actor B. We start talking about the messages that we exchange with each other, which are, again, very much like text messages. Text message is an asynchronous message. I send you a message. I can continue on doing whatever I want to do. You get that message. You react to it in some way, right? And maybe you send a message back to me. That's the kind of conversation that you have with actors. So I send you a text message. Maybe I'm asking you to do something, or I'm telling you something, and maybe you react to that in some way. Now, when it does get a message, actors can create other actors. So you can have like a parent actor that has child actors, or a supervisor actor that has worker actors. So when actors get a message, they can do things like create other actors. And they delegate work out to those other actors. So they can create some worker actors and then delegate some work out. So say it's like, I send you a message, you're an actor. In response to that message, you create some worker actors, and you say, worker actor, the first one is going to do task A, the second one's going to do task B, and the third one's going to do task C. And then you, the parent or supervisor actor, are waiting for those actors to send back the results of their work. Guess what? You just did multi-threaded programming without hurting yourself. Multi-threaded programming, like in Java, can be fun. This is the concurrency part of actors. Actors send messages to other actors. They're not waiting. Things are running concurrently, those types of things. This one's also interesting. When an actor gets a message, it can, in response to that, can decide how it's going to react to future messages. So, for example, say actors can have kind of a state, and this is by our design as developers. When we're designing an actor and the behavior of an actor, it's up to us how this works. But as an example, say we have an actor who's in an idle state or an active state. So when this actor first gets a message, when it's in an idle state, it goes, okay, I've been asked to do something, so I'm going to start doing that work, but now I'm in an active state. So if somebody sends me another message asking me to do something, I may respond right back and say, send a response back saying, I'm sorry, I can't do that because I'm busy. So in the idle situation, if I get a message, I'll say, yeah, I'm going to do that work for you. In an active situation, I'll respond differently. So it's kind of where actors can change their behavior, which is very, very powerful. And the only way the state of an actor is changed is in response to a message. And this is very different because, like in object-oriented, you can have a class that has methods on it, and other classes can invoke the methods on your object, and it can change the state of your object. In this case, no other code directly accesses any methods of the actor. It's all indirect through this asynchronous message that's sent to an actor. And it manages its own private state, which gets interesting because it avoids things like, and this is hard to explain, but it avoids things like semaphores and locks. When you're doing concurrent operations, you don't have to do these kinds of things as well. So that's kind of a quick definition of the actor model. I really like this. It says a lot. It's a lot kind of to digest if you've never really looked at the actor model, but it's really interesting. And then Kubernetes. I mean, everybody's been, this is the hot topic right now. But from my perspective, all I want is less drama to take my jar and run it somewhere. I just please run something for me. Don't make it hard for me. Just make it easy. And Kubernetes is getting really interesting in how that is done. And it does it quite well. And I'll show you a little bit, but kind of from the perspective of a developer. I don't care about the setting up a Kubernetes cluster. I really don't care about how the cluster works or anything. All I care about is how are my JVMs running in Kubernetes. That's all that really matters to me. And it kind of does that, where as a developer, I just really worry about running my code. But one of the big things that it gives us is elasticity and resilience. The nice thing is, and I'll show you this in a demo in a little bit, is you say, well, I want to run 3 JVMs in the cluster in Kubernetes, and things are running along, and say something breaks, some hardware breaks in the cluster, in the Kubernetes cluster, maybe a VM, a virtual machine goes down, and it just happens that your jar is running on that virtual machine. Kubernetes sees that and goes, oh, you asked for 3 jars to be running. There's only 2 running right now. I need to get that 3rd jar running again. So it automatically just handles that for us. And then on the Elastic side, you can set up your code to run where it can respond to things like if the CPU utilization of the currently running things is getting stressed, it can spin up more. So you can have more instances running automatically. So you can spin up more based on memory utilization or processor utilization. Really nice. So I want to give you a little demo. And I'm running an OpenShift cluster on my laptop. It's called MiniShift. I'm not as brave as Burr this morning. He was doing everything live over the network, and I'm not that brave. So anyways, it's pretty cool, though, for development. I can start up a console. And this is very much like, it's not quite like the real OpenShift console, but it's close enough. And what I've got is a project running. And so I've got this, we saw this in Burr's talk too this morning. There's this concept of pods. And a pod is where processes run, is one way to define it. A pod runs a Docker container or some kind of a container, and a pod can run 1 or more containers. That's kind of the molecular unit is the way I look at it in Kubernetes. So I've got a little application running here, and it's currently running 3 pods. And these pods are simple. Each one's running a Docker container, and that Docker container is just running a jar that I built in a project. Now, on the system, it's kind of nice. I can set up a network, and so I have an endpoint for this app, and this is a visualization of these 3 pods running. And you can see it's kind of moving around, things are happening, and I'll explain what all these little circles mean and everything. And by the way, anybody ever use D3.js? It's a JavaScript framework. It's awesome. I mean, I know enough JavaScript just to be a little dangerous, but I'm not a front-end person, but I was able to take one of the samples that D3.js has, and this is doing SVG and everything, all the pretty lines and everything, this D3.js framework is doing it. It's really cool. It's all running in the browser. But you can see things are happening, and I'll explain what's going on here. So the idea is that somebody in my company, when I first started showing this, they call it a crop circle. I don't think anybody outside the U.S. knows what a crop circle is, though. I keep asking over here in Europe, does anybody know what a crop circle is? And everybody goes, I don't know. Do you guys know what a crop circle is? Okay. A lot of places I've been is like, what's a crop circle? So a crop circle is supposedly where aliens have come, from some distant place and landed on the planet Earth. They find a wheat field, they put some weird pattern in the wheat field, and then they leave. And they don't talk to us, so it's like, okay, yeah, right. But in any case, so the circle is a way to show a lot of things, but one of them is there's a center circle, the kind of the central point, that really doesn't mean anything, but the big circles right off of it are kind of the root of things that are running in a JVM, in a Docker container, in a pod, okay? So I'm showing 3 pods here running. So there's 3 JVMs running and 3 Docker containers and 3 pods. And then the little circles are where I'm showing some Akka actors. So the most interesting ones are on the outside, on the perimeter, the blue ones. Those are representing, they're instances of an actor that represents where business logic is being executed in response to, say, commands to, like, say this is a shopping cart microservice. This whole thing here is one single shopping cart microservice. This happens to be running in a cluster of JVMs. And requests are coming in for different shopping carts, and there's an instance of an actor for each shopping cart. That's, like, so if all of us were currently, say, on a phone app hitting the system, each one of us would have an actor instance in the back end handling our shopping cart. That's what's happening here. The green circles are representing what's called, they're another kind of actor, they're called shard actors. And these actors are responsible for distributing the work across the cluster. So in the demo, there's always 15 of these green circles. So no matter how many pods are running, there's always 15, and I'll show you what they do and how they work. And then the bigger circles kind of represent the root of an actor tree on each JVM, and also some other things. The colors kind of tell me a little bit about what's happening in each one of the JVMs. They're not quite as interesting for our discussion here. And then the little pink ones are when actors are shutting themselves down. So what's happening is that the way the system is working, when instances of an actor are getting messages, the actor stays alive. When the actor stops getting messages, it shuts itself down to kind of free up resources. And this is kind of showing where it's just one microservice in a system of microservices. I'm not saying that every microservice you write is written this way. I'm just saying, this was a quick thing for me to show where on the left is a microservice system, and on the right is a kind of a blow-up of a single microservice system that happens to be written in this way. So let's go back to the running system. And one thing I can simulate is a failure. So this is the resiliency part that works, and it kind of shows the relationship between what happens at the Akka level when there's a failure and what happens at the Kubernetes level when there's a failure. So I've set this little app up. If I click one of these circles, it should trigger kind of a failure where the JVM actually shuts down. And now we're down to 2 JVMs running in 2 pods, okay? But very quickly, you can see we're back to those 15 green circles, those shard. So there were 5 on one of the node that went down, and now they're redistributed to the remaining 2, okay? So from a system standpoint, the actors have recovered very quickly. But now you see a 3rd pod has popped up. This is the Kubernetes part. So Kubernetes saw there were supposed to be 3 pods running, but for some reason, we dropped down to 2. And it goes, oh, I need to start up a pod. So this pod starts up. The JVM starts up in it. The JVM starts talking over the network to the other pods, the things in Akka, and they reform a cluster. And then what's happening at the actor level, the shards go, oh, we got more capacity. Let's rebalance the load across the cluster, okay? So another thing I can do, though, is say there's a spike in traffic, and we need to scale up. So I'm going to simulate this, where I'm just going to manually do it. But you can, a feature of this is of Kubernetes. You can set up Kubernetes when you define what's called a deployment, or you can define it so that you can say if the CPU threshold reaches a certain percentage, then that's a trigger to scale up. So I'm going to just simulate it. Say this microservice is getting hit hard. The 3 pods that are running are getting hit heavy on CPU. So Kubernetes goes, oh, I'm going to add a couple more pods. So I'm going to scale up to 5, all right? And what we'll see in the demo part here is that Kubernetes, and I'm not using Growl, so that this is a little bit slower startup here. It's just a Docker image coming to life. a Docker container coming to life, and then the JVM runs, and then the JVM starts up, my code starts running. I got some Akka code that triggers joining the cluster, and you can see a fourth one's popped up, and the shard's already moved over to it. The load's getting rebalanced, and there's the fifth one. So what's happening is Kubernetes goes, okay, this app needs some more capacity, so I gave it some more capacity. At the Akka level, it goes, oh, yahoo, I got more capacity. Let me start moving some of my actors over there, okay? So it's a little bit of things happening in the Kubernetes level, a little bit of things happening in the Akka level. So now we're running along, the load should kind of rebalance, and this is deliberate. Akka doesn't kind of immediately start shifting things over when it gets more capacity. You can see it's kind of more gradual, but I think we rebalanced because there's 15 shards, we got 5 pods running, and there's an even distribution of 3 shards per pod, okay? And then say now the peak load is over, and Kubernetes goes, all right, you don't need all this capacity. I'm going to scale you back to 3, and that happens really quick. Kubernetes just kind of shuts down the JVMs. It's a clean shutdown. It doesn't kill it, but it's a clean shutdown. And then at the Akka level, it goes, oh, lost some of that capacity. Let me distribute the shards. Okay? So a lot happening here, but hopefully the visualization gives you a little sense of what's going on at the Kubernetes level and at the Akka level. And the term reactive is very, we heard it this morning in the keynotes, but often when you hear the term reactive, it's reactive programming, which is great, but there's also reactive systems, and that was alluded to as well this morning in the keynotes. But in a reactive system, the principles are very simple. You want to build a system that from the perspective of the users of the system's always running. It's just working. But in order to do that, there's 2 other things, that the characteristic that the system should have. It should be resilient to failures. Failures are just part of the architectural feature of the system. That's kind of what I was trying to show you. Pods are going away, and Akka is reacting to it, no problem. And it's elastic as well. When you need more capacity and the system scales up, the code itself can react to that as well. I've got more capacity. Let me move some of the work around the cluster. So that's the kind of the basic characteristics of a reactive system. And that's what we're kind of getting from it's kind of a symbiotic relationship between Kubernetes and Akka. Again, Kubernetes could care less about Akka, but Akka really loves running on Kubernetes. So let me show you the project. There's I've got a Java project here that's running. I'll give you the link, the GitHub link at the end of the talk for this project, but it's just a simple Java Maven project. I've got a POM here, and some people ask, well, why aren't you using Growl or whatever, or Grails or whatever, but it's like, but I wanted to keep it pretty basic. So the only thing I had to do for this Maven project to make it work with Docker and Kubernetes was I needed to there's this one plugin that gives me a self-contained jar. It's just a Maven plugin. The more interesting one is there's another plugin. I don't need a Docker file. For those of you that are using Docker, there's a plugin that I can use that builds the Docker image. So I can just do a Maven clean package Docker :build, and it builds a self-contained jar, takes that jar and throws it into a Docker image, and it's ready to go into Kubernetes. The project also contains some Kubernetes files. What I want to show you is this deployment file. So this is a YAML, and there's different ways for doing this, but the YAML basically is declarative. So you're not saying how to run things in Kubernetes, you're saying what you would like to run. So basically, all I'm doing here is saying, I'd like to run 3 instances of my, where is it at? Docker image. Okay? So there's a lot of, I don't know what everything that goes in this file. I don't want to be a Kubernetes expert. I just want to run my jar, right? So I took a template, filled in a few things, and it worked, and I was happy, right? But basically what I'm saying is when this thing starts up, when I deploy this app, run 3 instances of it, and here's the image that I want to use. So if I build a new image with a different version, different tag, then I just change this file, and there's a command interface where you can give this file to Kubernetes. And the cool thing is, once this thing has already been submitted to Kubernetes, if you resubmit it, it's going to diff what it currently has and what you just gave it, and it's only going to do what's changed. So if the only thing, say, that I've changed in this file is the image, say it's a new tag, a new version of the image, the image, then the only thing this is going to do is trigger a rolling deployment of my image. It's going to shut one pod down. It's going to start up a new one with the new image, and it'll go one by one by one and roll through all of them, pretty much for free. It's very nice. I just want to show you a little bit of the main of this project. I've got this method where I kind of get things rolling, and one of the first things I do is I start Akka, which is kind of like one line, and there's a relatively simple configuration file behind this as well. There's not a lot to it. The real magic happens, though, in this little method I wrote that's called start cluster bootstrap, which is down here. And it's just, all I'm doing is calling a couple different things that are part of Akka. And so this bootstrap part is pretty interesting, because what happens is, a JVM starts up, and it needs to look around and see, well, are there other nodes in my cluster or not? So the way it works is that these 2 lines of code trigger a whole sequence of events where the JVM starts up, it starts up Akka, it invokes the cluster bootstrap. The cluster bootstrap makes an API call to Kubernetes and says, are there other pods out there like me? Kubernetes gives back who's ever out there. And basically what Akka wants is the network addresses of the other pods. So it takes those network addresses and then it starts communicating with them. And what's happening, and this is all happening in Akka, is basically saying, hey, I want to join the cluster. So there's kind of this whole sequence of events that occurs where these JVMs start talking to each other over the network, and a new node joins the cluster. So in this project, I added a bunch of logging where you can kind of see when things are, as this stuff is happening. It's kind of fun to watch, to get kind of if you're new to this, and even if you're not, it's fun to kind of watch nodes joining the cluster and so on. But just a couple other things I want to show you is that here's an example of creating an instance of an actor. And I'll show you some actor classes in a little bit, but this is kind of like doing a new on a class, but it's kind of the Akka way of creating an instance of an actor. So I'm just saying actor system .actor of, which is a method that creates an instance of an actor. Here's the properties of this actor that I'd like you to create. So properties is basically going to invoke the constructor of the class. So if there were constructor arguments, they would be arguments passed to this props method. Okay. Basically, what it does is it goes to that class, creates an instance of it, but it's creating an instance of that class as an actor. All right. Down below the next line, I'm doing it again for another actor, but this time I'm getting back a result, which is called an actor reference. So every actor has basically an Akka URL. And if you look at it, it's like Akka : / host name, port, and a path. And the path is the path to an actor. So actors have a path. And every instance of an actor has a path, just like web pages have a distinct paths to it. So this actor reference is what is used to send messages to that actor. So like I said earlier, external code never directly accesses a method of an actor. It can only send it messages, which are objects, via the actor reference. So the entity actors, those blue actors, the ones on the perimeter here, like I said, those are the ones that are actually invoking business logic. And what I'm trying to show here is how do you interact, like how does an external client interact with specific instances of an actor? So in this example, I've got, say you are interacting with entity 64, which is like the ID, like the shopping cart ID, or your bank account ID, or an IoT device ID, or whatever it is. It's some unique identifier. And I am interacting with entity 17. Now, our HTTP requests from our clients are coming in through some kind of a load balancer, which you can get from Kubernetes, which is pretty cool. Your request is coming in and landing on one of the running JVMs. It's kind of arbitrary when you're going through a load balancer where your HTTP requests are going to come in. So it just so happens your request and my request are both landing on this pod running a JVM in the top left. Now, your request is for an entity that happens to be running somewhere else in the cluster. So there's a series of actors that are involved, and these are kind of out-of-the-box actors that come with Akka. But it's kind of like there's actors that are known as router actors. So it's like, say you're the shopping cart, you send me an HTTP request, I get that HTTP request, I create an object from that request, and then I send a message to, say, me as a routing actor. My job as a routing actor is to figure out where is entity 64 in the cluster. And there are other actors that do this. I won't bore you with all the details, but it's kind of cool if you're interested how it works. But essentially, it'll find out that, entity 64 isn't running in my JVM. It's running in this other JVM. So it just takes that message and forwards it across the network to another actor on the other side that's like this routing actor, and this other actor on this other JVM gets the message and goes, this is a message for entity 64. Is that one of mine? Oh, yeah, it is. What shard does it belong to? I'm this shard down here. I'm going to forward the message to the shard. The shard gets it and goes, is entity 64 running right now? Because it's supposed to be one of my children. If it's not, the shard actor is going to start it. If it is running, it just forwards the message. And then ultimately, the actor gets that message. Now you look at this and go, oh my God, there's all these things going on. But this year, Akka is 10 years old. They've been building Akka to do this for 10 years. So sending messages over the network is highly, highly optimized. In fact, there's a new release coming out. It's like release candidate 2 right now, where they've even optimized some of the network trafficking even more to get more throughput. But Akka is built to do this on a scale of millions of actors, like millions of actors per JVM, and millions of actors talking to each other over the wire as well. Okay, so actors are really very small, very discrete things typically, and I'm only showing you a demo here with like 100 actors or so, but typically, it's thousands or hundreds of thousands of actors that often an actor system has. They're very fine-grained and they do a lot of work. Now my request is coming in, same thing. That actor, that first routing actor gets my request. Is entity 17 one of mine? Yeah, it is. What shard belongs to it? Okay, let me send it to the shard. Shard does the same thing. Yep. If it's not running, start it. If it is running, send it the message. That type of thing. But then when something happens, say where we lose a node and everything changes, the actors themselves adapt to this. So say Kubernetes scaled this back from 4 to 3 nodes in the cluster because we don't need that extra capacity. So it did it on kind of at the coarse grain level. Kubernetes is kind of controlling our JVMs. The actors are controlling what's happening in the collective group of JVMs, right? So this is the idea that if we're scaling up or scaling down, the users don't perceive those changes. From their perspective, the system just keeps working, keeps running. So let's take a look at that entity actor, the code for that. It's just a class. It extends an Akka base class. No big deal. There's only one method that is required to be implemented, and it's called create receive. And this method is building a receive object, which there's a builder pattern that is available from Akka to do this. And basically, it's just kind of doing a pattern matching. So what's happening here, this code is responsible for handling incoming messages. And the messages are just Java objects. So a message comes in, and I'm the one who wrote this code. I look at it, I set it up. Is the object what I call the command object? If it is, I'm going to invoke this command method. Is it a query object? I'm going to invoke the query method. So the command method, for example, is right here. And this is just my code. So I've got the message. I know it's a command. My code starts looking at it, and I look at it and go, is this object I call entity null? If it's null, that's a clue to me that this is the first time since this actor started up that it's got a command message. If it's not null, it knows that it's a subsequent message, that the actor's been around for a while, it's been receiving commands. In any case, when I do get a message, one of the more interesting things it does is this is the code sender.tell is saying the sender method is when I inherited from the base class. It gives me the actor reference, that actor URL of whatever other actor sent me a message. So I'm saying, all right, hey sender, .tell is sending a message. And the .tell, I build an object, and then which is this new entity message, command act, blah, blah, blah. And at the very end, I've got this self. And self is just saying it's like from. It's like you're sending a message where it's got the from address and then the body of the message, okay? So this other actor could be, I don't care where it's at. It could be running in my JVM, or it could be running in another JVM in the cluster, in another pod. This code doesn't care about that. All it's saying is that, yep, I want to send a message to this actor. Boom, that's it. One line of code. Same line of code, doesn't matter if it's over the network or not. So if it goes over the network, what Akka is going to do is, it serializes the object, sends it over the wire, comes on the other side of the wire, deserializes it, and forwards it on to the destination actor. We don't write any code for that. That's all handled by the Akka Toolkit. There's, this example project, I wanted to keep it simple. It's doing a lot of interesting things, but I wanted to keep it simple. So it doesn't do it like any persistence. For example, it's not hitting a database. I have other sample projects that I'll give you the links to that do persistence, but these don't. This one doesn't. So the idea is that, we're running on, if we're running on one pod, the visualization showing one big circle. If we're running on 3 pods, the visualization is showing 3 big circles. And I'm trying to, the visualization is trying to show how things move around when things happen. The fun part of this little project is that you can see this happen. You can, my intent was you can, clone the project, build it, run it. And I've done workshops with this, for example. We got in a workshop, and the idea is you guys install Minikube or Minishift or get some form of Kubernetes running on your laptop, get the apps installed, get it running, and then when you get the little circle running, it's like, aha, it's all, I'm up and running, and now you can start playing with it. You can, scale up, scale down, kill nodes, that type of thing. And then, of course, you can start playing with the code itself. When a pod goes down, like I'm showing here, we were showing that also. And just again, those green circles that are shard actors, their job is distributing the load. So what I'm trying to do here is show you, say this pod that's running in the top left, it goes down. So we go from 4 pods down to 3 pods on the right. And I'm trying to show, I just took snapshots. I had it running with 4 pods, took a snapshot image of the screen, killed a pod, or spun down a pod, and then took another snapshot. And in the demo, if you mouse over one of these circles, they keep moving around on me, I kind of highlight its ID. So shards have IDs, and each entity has an ID. So you can see where it, again, things are moving around, but you can see what entities are popping up where. So where an entity pops up is all using kind of a sharding algorithm, like a hash divide type of thing for distributing entities. So entity 57 will always be on shard 3, no matter where shard 3 is at, okay? So there's this one thing called cluster-aware actors. I'm going to kind of zoom through this and show you something that's interesting in the way this example demo app is working. So the idea is that when the system's running, I don't know if you can see it. I think it shows up. Yeah, when an entity starts up, it shows for a little bit as dark blue. So you can see some that are a little bit, the blue circle's a little bit dark. So that means it just started. And of course, when they've been around for a while, then they go a little bit lighter blue. And then when they stop, they kind of poof out of existence. And the situation, though, is that my web client is actually coming in here. I use a color to kind of tell me where the web client's coming in. Because I'm just hitting a URL, okay? But an entity actor popped up on another node in the cluster. Well, the way this client is working is just being, every 5 seconds, the web client is asking, just doing through a WebSocket, it's asking for, give me the current tree. This whole thing is a JSON tree coming up to the client. Well, how do you build this JSON tree where things are happening all over the cluster in multiple JVMs? So the solution to this was actually quite simple, where what I'm showing here is like, where I have the arrow, it's dark blue, it just started. And I'll show you the code in a minute, but what happens is that actor sends a message to another actor to say, hey, I've just started. This other actor, the one in the big circle, is what I call a cluster-aware actor. It knows, because I wrote it, that there's instances of itself, one instance of itself in every pod running in the cluster. So it uses that to communicate with the other ones and say, hey, entity 67 just started on my node. So every node in the cluster has the same view of the tree, right? So the code to do this is actually pretty simple. So in the entity actor, when an entity starts, I call this method, just a method I wrote called notify start. And notify start, what it does is it builds a message, just an object, a Java object, and then it does a tell to this actor that I called HTTP server, which is that big circle, an actor in that big circle. The HTTP server actor is right here. Built the same way, extends the base class, has a create receive, and it's set up when it gets this action, it sees an action message, it invokes a method I called action entity. And in this, I look at the message and I look for, does the message contain a string start? And this is all by my design, it's just simple design. So I load it into a tree. I got a simple Java tree object that I'm using here. If it's a stop, I remove it from the tree. But then it looks at another field in the message and it looks and says, is the forward field, the Boolean, true? Meaning, should this message be forwarded to its counterparts? So, because if it goes to a counterpart, you don't want the counterpart to forward it again. Otherwise, you just get this message storm and they'd all keep messaging each other, which I did. When I first got this working, I had some screw up in my logic, and I just had this message storm happening where everybody just kept forwarding these messages. But in any case, if it's true, it's going to invoke this method called forward, and this is where the fun part starts. So one of the things that I inherited from my base class is the ability to retrieve information about the cluster, the Akka cluster. This is Akka stuff. And you can see the cluster object here that I got has a method called state, which I really don't care about, but what I do care about is state can tell me the members that are currently in the cluster. And it gives me a list of those, so I can loop through that list, just a simple list. Then I just take a quick look at the member. Is the member me? Because I don't want to send myself a message. I know that this entity actor started or stopped. But if it's not me, and that other member is in an up state, because members in the Akka cluster have a pretty elaborate state. They can be starting and stopping and leaving and all these different things. I just want to talk to ones that are up. If it's up, then I forward the message, which comes down to this other method. And here I'm basically just building a actor reference. And it's kind of like I take the host of the other member and the port of the other member, and I'm taking the path to myself, and I'm appending together to build a actor reference. It's just kind of building a URL. And then I just do a tell. And then, so this is looping through, like if there's 4 members running the cluster, the one actor gets it, and then loops through and sends it to the other 3. So this is how it's communicating to all of these actors, one per JVM, what the tree looks like. Okay? And, it's doing some interesting stuff. There's network messaging going on. There's, what's the current state of the cluster, all these different things that are happening with like 10, 15 lines of code. And it was my little, just knowing the fact that I could do this as a pattern in building an actor system, it was just my little invention for doing this. This cluster-aware actor kind of thing, though, is very, very powerful, and that's why I wanted to try and introduce it in this demo app. There's also the concept of a cluster singleton. This demo app has that in there. I won't bore you with the code. It's pretty simple. But the idea is that there's a one instance of an actor for the whole cluster. And this is where if you need to have like one place to make a decision across the whole cluster. It's common enough that the Akka team created this for us as a pattern. And the idea is that if the singleton, what's called the cluster singleton, is running on a node that goes away, fails for some reason, the cluster singleton is started up somewhere else in the cluster automatically. We don't have to write any code to do that. And then cluster sharding, which I've been showing you, is the basis for what's called Akka persistence, which is the boring name for those of you that were in my talk this morning about event sourcing and CQRS. This is the kind of the framework for building a event sourcing and CQRS system. Each entity actor is persisting taking in commands and persisting events for specific entities. And the idea is that, and this is provided with what's called Akka persistence, is the persistence of events to an event log, like in Cassandra or whatever your favorite database is. So this is just an example of event sourcing where events have like a certain key and a value. The key is usually like a sequence number or time, and then the ID. It's usually some kind of concatenation like that. Something that makes it unique. So it's like all the events for entity 76 in red here. You can see there's 3 events for entity 76, but they were at different times. And there were different actions like add item, change item, and so on. So that's the idea that there's this way of having traffic being routed across the cluster without a lot of heavy lifting on our part as developers. And kind of wrapping up, the whole idea is that Akka has this beautiful relationship with Kubernetes, but Kubernetes doesn't care. But we don't care because we love running on Akka clusters on Kubernetes. It's a great platform for us. And it gives us that reactive system characteristics. So here are the links to the projects. The top one is the one I was just showing you. And the README has information in it for running it, or setting it up and running it on Kubernetes cluster like Minikube or Minishift on your laptop. And I just finished adding some stuff for running it into something like OpenShift Online, a real OpenShift environment, which is running Kubernetes, of course. These other projects are similar. They're all Java. They're all simple Maven, but they kind of go from a very basic cluster project where you can clone the project, build it. It's not using Kubernetes, but you can run a cluster of multiple JVMs on your machine and play with it. There's some logging in there to kind of show you what's going on. And then each project successively builds up and gets a little bit more complicated, but they're kind of building on each other. The last two, you can see that it says persistence, so it needs to use a database like Cassandra, okay? Which is easy to install if you want to run it on your laptop. And if you're interested a little bit more about actors, I've got a little, I'd rather call it a comic book than a booklet, because it's lots of pictures. Some words, but lots of pictures. I like visualization. So the book it's not code or anything. It's free to download, but it's just kind of give you an idea of the kinds of things that you can do with actor systems. The different patterns. And it was a lot of fun, and it's a quick read, and it's free. And that's it. Thank you very much. I have no idea if we have time for questions or not. Of course, I'll be up here if you have any. But 10 minutes? Okay. Yes, sir. What's the difference between a shard and a pod?
Yeah.
Okay, good question. So a pod is, the way I think of it is it's running a whole JVM, all right? A shard is just a conceptual thing, but it's implemented as an actor, where a shard is where it's used to distribute work across the cluster. So the shard's role is that certain actors' IDs hash to a particular shard ID. It's just math, right? So and shards are set up to move around. So like there's always a fixed number of them. So in the demo I had 15. So even if we scaled up to 15 pods, there would be one shard actor per pod. If we scaled up to 20 pods, we'd be wasting 5, right? Because I don't have enough shards. So typically you have a lot, like a 10-to-1 ratio between the number, the maximum number of shards and the maximum number of pods you want to run. But the shard actors, its job is to just run a subset of entity actors, no matter where that shard actor happens to be distributed to. So if the shard's running on, say, one pod and that pod goes down, that shard actor will be started up somewhere else in the cluster, and then the entity actors that go with it, that mathematically hash to it, will be started there as well. Okay? Any other questions? Let me just say this. It's really fun to kind of look at the actual mechanics of what's happening in this system. Even as just an intellectual exercise, if you try to kind of work out how the system's working, how it's doing the distribution, how it's kind of shifting the work around and so on, to me it's a fascinating, the mechanics of it is kind of a fascinating insight into some of the ways that we use distributed systems. And that's why when I came across Akka, I just fell in love with it because it has these capabilities I just couldn't even think of doing without it. So to me, it's the coolest thing I've ever seen. And I've been coding for a long time. I probably started coding before most of you guys were born. And I love coding, and when I came across Akka, it was just blew me away, just totally blew me away. And it was so much fun to build these kind of systems. Yes, sir.
Is it possible to run this entire framework without Kubernetes?
Yes, very good question. Thank you. It is possible to run it without Kubernetes. The Akka cluster has been around. I think it kind of came out as soon as Kubernetes started to come out, but Kubernetes didn't kind of hit most people's radar until like the last 2 or 3 years. So like when I first started using Akka clusters, we were just running them on VMs. and we were managing the VMs ourselves. I would have loved to have had Kubernetes instead of having to manage all the VMs. But no, it doesn't need it. In fact, the other demo apps or the applications that I showed the links to don't use Kubernetes, but they'll run a cluster. So the question is, does it run Akka streams? In the demo apps that I have, it's not using Akka streams, but of course you can. So Akka streams is a different way of, it's like a flow-based way of doing processing without actually writing actors. And it's very, very popular. A lot of people use Akka mainly for Akka streams. But no, the demo I'm doing, it's not using that. It's basic actors. Yes, Akka streams can definitely run in a cluster. And they're actually been enhancing that to make it better, more things that it can do across the cluster. Because typically Akka streams ran, within a single JVM. And now they're kind of making it where you can branch out a little bit more. And the reactive streams, we were heavily involved with the whole reactive streams initiative as well. Okay? All right, thank you. Thank you very much.